Simple harmonic motion and the reference circle. I would recommend that you have a decent understanding of trigonometry, probably around the pre-calc level, because it does use pre-calc identities, and um, and hopefully calculus, because if you understand calculus, you can differentiate without having to prove the functions or the velocity function, because you can just differentiate the position function. So before we start, it's good practice to know um, the stuff, the mathematical formulas, because they will be used here. So 1 second. Okay, so let's talk about our reference circle and why it exists. So we're gonna relate it to trigonometry. So remember in chapter 8 we learned about essentially momentum. Um, so let's start with something moving right here. So let's say assume the velocity is constant. This means from here to here, and we track its shadow. We see that it has a simple harmonic motion because it goes back and forth and back and forth. And we're going to prove it in just a second. So if we just watch the shadow here as it goes around, it's going to go right here. So if the position's right here, um, then it's going to be right there, and the position's right there, it's going to be there, and then the shadow's going to be right there. But also note that only the x position matters here. How high the ball goes doesn't really affect the shadow. Um, though in real life, if the sunlight is beaming down on this said motion, then yes, it will make a difference in the size of the shadow. But here we're just going to assume that the sun is one point in space and is in a 2D plane. So, yeah. You can watch its shadow on the x-axis, so yeah, all this nonsense. I mean, not nonsense, but just all this stuff I've already explained. So, I don't know why the book goes from A to R. So A standing for amplitude. But remember, amplitude is the maximum position function, which is just going to be R, because the amplitude's maximum is the circle's radius. So I don't know why they switched from A to R, but probably to give you a better understanding of how sinusoidal functions work. So sinusoidal functions are just any function in the form a cosine bx minus c, a cosine, if I remember properly, bx minus c plus d. Actually, you see this a lot in textbooks, but this should be the proper notation here, just so that this remains a vertical stretch. I mean, not a vertical stretch, vertical translation. So this is the proper form here. So you'll see this in pre-calc, which is why I said it's pretty important. So so that's all we have to know for why or how the circle relates the um, to the simple harmonic motion, which again is just something moving in a straight line back and forth, essentially. So if you take a circle here again, and the radius a, because it's again the amplitude, the angle moving would be theta, and the projection would just be a cosine theta. So that's pretty simple stuff. That means at any position on here, you can calculate the x position. So if the angle theta was this big, so let's actually erase all this stuff. Remember, the amplitude stays the same. Oh, wow. Okay, so there we go. Yeah, that looks pretty bad. Let's just go right there. But essentially, we can calculate what the x component is if the a is right here. And the x component would be this negative x position. So that means we can rewrite the function of the position as a cosine theta, uh, where where this will always give you just essentially how long the x length is. And this works everywhere around the unit circle, because if it's past 90 degrees, for example, it will switch signs and turn negative. So I think that's pretty beautiful. So that's all we need to understand for now, because I'm gonna go into the different um, how they derive the function. So again, that is just that. But remember, theta is just angular momentum times t, because this is just rads per second. Or I keep saying rads. Actually, yeah, rads is the right notation. Seconds. Although this technically does work with degrees, so if you convert this to degrees, it works as well. But we use rads just so we can multiply it by the radius to get the arc length. So this just leaves you with rads. So essentially, this formula is the same as theta, And we can turn this, oh, actually, this should be x of theta, from x of theta to a function of t, such that it becomes a cosine wt. I say w, but I really mean omega, which is just how many radians you're doing per second. Pretty simple stuff. Again, this is just a sinusoid in the form a cosine bx plus d. Notice I don't include the c term. Or actually, I shouldn't even include the d term because it's not present in this function. So it's just in the form a cosine bx. Where a is the amplitude, of course. So the amplitude would be, I guess, the spring's, half of the spring's length in this case. Half of the spring's length. Not half of the spring's length. It would be half of a simple harmonic motion line. So one full circle is one full oscillation as the ball moving around the circle goes around the unit circle. It's pretty simple. So F equals 1 over T. I should probably write like 1 cycle over T, which essentially gives you how much cycles you are getting per second, which is just 1 over, or actually it would be 1 over cycle and then period or time to do a cycle. So let me just edit this just so it's a little bit less confusing. So it's going to be 1 cycle divided by amount of time to elapse a cycle, or elapse 2 pi, I guess. But we're not working in radians here, we're working in cycles. And again, omega is just 2 pi over t, or the angular speed. So this is where the proof gets a little bit sketchy here. But bear with me, because you will need some pre-calc. And maybe they don't even teach you till calculus, but we're going to go into sine double angle, or sine sum identities. So let's take that circle again. And let's go here. So remember that we have a function of time of the position. Yeah. Okay. And remember that the velocity, or the tangential velocity, is just equal to omega times r. Because remember that this is rads per second, and arc length is going to be equal to rads per times radius, which essentially gives you how long the arc length is. And note that w is rads per second, so it becomes in this, and we'll just divide seconds on both sides, giving us velocity, or tangential velocity, is equal to this part right here. So again, it's pretty simple stuff. And also note that as the time goes to 0, the instantaneous velocity looks a lot like the arc length, which is why we can use this formula flawlessly. So that's what we have here, and now we have to understand how fast the x position is changing. And we know how fast the x position is changing, or the velocity of the velocity in the x direction. But remember that the ball, like let's say at this point, the velocity always points perpendicular. So we can treat this as theta plus 90 because this thing is perpendicular to this velocity vector, such that this angle here is 90 degrees. So essentially, we can find the projection of this projection of the velocity vector onto the x-axis just by adding 90. So that's pretty simple stuff. So it's just going to be a cosine. Or not, yeah. Cosine. Theta plus 90. Because again, it's just, we're working in thetas here before we get to the actual position here. This is just the position function using time, but we're going back to thetas. So let's work with this identity here. Remember cosine? I'm going to do my best to recall my trigonometry. So that should be cosine theta, cosine 90 minus sine theta, sine 90, I believe. But cosine 90 or sine 90 is equal to 1, and cosine 90 is equal to 0. So it's just going to be minus sine theta. So that's essentially where we get the logic here. It's not going to be using the simple trigonometric identities you learn in geometry. So then it just becomes a sine theta, negative sine theta. But recall that this will give you the angular momentum, or the angular velocity. So to convert to So to convert to um, tangential velocity, you'll just times it by a radius r. So now we get the form that the velocity at any points of the x position is just equal to negative a sine theta r, or negative a sine r theta. But remember, theta is just wt, so negative a r sine wt. Oh wait, hold on 1 second. Yeah, I meant omega because r is the radius here. Yeah, that didn't look right. So now this is the formula that you have, negative aw sine w theta. Um, so now we have Vx. Let me erase all this stuff here. So the velocity of x at any point, which is essentially the velocity, of the mass on the spring, is equal to negative aw sine wt, or just negative aw sine theta. So that is that. But something beautiful here happens using calculus, because you can think of it geometrically, but I hate geometry, and I'm sure a lot of you also hate geometry. Guess what? A is a constant here, so you can just pull that out. So d over dx of a cosine theta is, or a cosine wt here. I guess you could do t as well. It's going to be the same result, and I'll prove it to you. So we'll have to chain rule that. So that is the same as d over dx of cosine wt, which is just going to be a negative a sine wt times w, because t is the function. Oh, actually, it shouldn't be x. It should be t. We're differentiating with respect to time. So it becomes negative a w sine wt. So, if you're smart and you take calculus, that should be a lot easier than the geometric proof I just showed you. So A equals amplitude. So let's use some logic here. And if this is the velocity, then what I can actually do is I can calculate when it won't be moving. So that's just setting it equal to 0. And let's solve for it. You can't solve for it like here. I'll show you how to solve for it. Well, notice that this is all products, so we can use the zero property product rule, but I'm just going to use some logic, or not logic, I'm going to show you with algebra. So we're just going to divide negative a on both sides, such that it's w sine wt. In fact, let's divide w on both sides as well. So it's equal to 0 divided by negative aw, but this is just 0 sine wt. And the inverse sine of both sides is going to be equal to wt equals 90 degrees, I believe. Wait, 90 degrees. No, it should be 0 degrees. 0 or 180 degrees. 0 degrees or 180 degrees. Because that's when the sine theta is at 0. So whenever this, which is the same as theta, is equal to 0 degrees or 180 degrees, that means the spring is not moving at all, essentially. And you can understand that logically as well, because as the object is moving around the circle and it's at the ends, this has to have a change in velocity. So it has to go from a positive velocity to a negative velocity. And as we know, in kinematics, that means, or actually, not even kinematics, intermediate value theorem. There's intermediate value theorem. There's mean value theorem. You differentiate and set to 0. That there has to be some point in the middle where the velocity is equal to 0, and therefore it's not moving at all. Pretty beautiful stuff there. So calculus really comes into play at there. So that's why velocities are at the ends. So now we're going to get to acceleration. So let's go over what we've learned so far. So what we learned so far is that if we take that mass on a spring, there's no velocity at the ends. We figured out how to calculate where the shadow is at any given point, which is just a cosine wt. And we also figured out that negative aw sine wt will give us the velocity at any point. So now, how do we get to the acceleration part so that we can start working with acceleration? Any smart person would probably differentiate this again. And let's see. I actually didn't check this part, but let's see if it's flawless. So the derivative of the velocity function, and we're going to differentiate with respect to time. Actually, to make it simple, let's differentiate with respect to theta and just switch it back to wt. So the derivative of aw sine theta is just going to be equal to, actually, you know what? Let's differentiate with respect to time, just to make things easier. And remember, w is constant, so we could just pull these out. It's equal to sine wt. So this is not derivative. I'm just denoting what the function is. And then we could differentiate sine. So it's going to be negative aw cosine wt times w, because we have to chain rule this inner function such that the function becomes negative aw squared cosine wt. So let's see if this is right. A cosine wt. Yep, and it's right. So yeah, just simple stuff here. But before we do so, let's prove it geometrically as well, just because if you don't understand calculus, I hope this will give you a better idea of what it is. So remember that there always has to be a tangential, or not tangential, a centripetal acceleration towards the middle. So the centripetal acceleration always points this way, but the velocity vector is pointing this way. But the position right here is always going to be essentially, how do I say this? Okay, so the position is always just going to be theta plus 180, because this acceleration always points opposite towards the displacement. So like, for example, if your object is right here, your radius vector, or not vector, your radius is right here, but your acceleration vector points inwards, such that this is actually a positive acceleration, depending on if you denote the right side as positive. So it's a little bit difficult to understand, but remember that a we defined as omega squared r. This proof is pretty simple. Acceleration equals v squared over r, but we know that v equals wt, or not wt, it would be wr. So we just plug that in there, which is just going to be equal to w squared r. So that is the derivation of that. They use a again, and projecting onto the x-axis. The ax is equal to negative a times w squared cosine wt. So same exact function here, except we add so w squared r will be the acceleration, but now we have to make it point towards, or we have to project it on, and to do so it would just be cosine theta, but also we have to make it negative because it would be cosine theta plus 90, and cosine theta, oh wait, no, it would be cosine theta, and since the cosine is always pointing in the opposite direction, it's going to be negative. There we go. That's what I was trying to say. So this becomes your acceleration function. So now all that simple stuff was simply a derivation to help you understand kinematics on a spring, essentially. So velocity is equal to 0. That's all we learned so far. I mean, that's not all we learned. We also learned that the position function is just going to be a cosine wt, and the velocity is going to be equal to negative aw sine wt, and then we learned that the a of t is going to be equal to negative aw squared cosine wt. So that it was only to establish these three functions right here. So the book really does get into a lot of depth right there. Again, they use this other derivation there, and why springs produce simple harmonic motion. Now this is where we get to Hooke's law. So F equals kx, but we also know that F equals ma. But they also use the restoring force here, so it's going to be negative kx. So negative kx is equal to ma, because we're trying to find out what the spring's restoring force is. So essentially, this is the force the spring is exerting on the mass. But we know that a is equal to what we calculated before, which is just going to be negative w squared x. Oh yeah, I forgot to mention. So if a of t is equal to negative, I'll just use r, negative rw sine wt, negative r squared sine of wt. Oh no, it was cosine of wt. Yeah, it would be cosine of wt. Then remember that r cosine wt is equal to the position function, so it would just be negative r, or negative x w squared, which is what we can substitute in here for mx w squared, and the negatives cancel out, and now we can calculate this. Well, you can calculate multiple things here. You can calculate the spring constant, but the book primarily focuses on the omega here. So let's solve for the omega, and the omega would just be x divided by v square root. So essentially, this omega tells you the speed, and if you want to do the reciprocal, then it would be wait, sorry, this looks a little bit confusing. All right, there we go. Then the period is going to be equal to square root v over x, which is essentially the time for it to go from here to here and back to here. So this omega essentially sets up the speed, or the amount of time it will take for it to oscillate back and forth. Hence the name, um, hence the name, or hence the sinusoidal function, and the name of the time, or not the name of the time, or the period. That's what I'm saying. So the omega w here represents how fast the system oscillates back and forth. Because when you chain, I mean, it's also simple calculus, because when you chain roll out the position function, a higher w will indicate a higher rate of change, or a higher proportionality constant. And because omega represents how fast the object is moving around the circle, 1 over omega will essentially give you the amount of time it takes for any object on a circular motion to make one full cycle, and one full cycle in the circle is one full cycle on a spring. So pretty intuitive math stuff here. So since spring stiffness matters, so this is just extrapolation of this. In fact, I think we do have one more derivation. Oh wait, yeah. Negative k over m. Oh shoot, sorry. Okay, and then we cross out the x's here, giving us negative k over m. That was a k. I didn't read it properly. So this is essentially the derivation here. And we can also calculate k after. 1 second, let me make this cleaner. And then k is also equal to w squared x. Wait, w squared x. I'm sorry. K is equal to w squared v, which is essentially what it was, right? This is m also. Sorry, I don't know what's going on with my algebra. So all I did was square both sides here and then multiply the m over. So it becomes k equals w squared m, as to calculate the spring constant. So this means a mass and spring stiffness matter, because the larger the mass, a greater k. But also, if we look at the omega here, the omega is the spring constant divided by the mass, and then the square root of that, which essentially gives you the angular momentum. So the higher the spring constant, using some knowledge of how functions work, given all things are equal, will mean a higher angular momentum. But a higher mass, if they're increasing at the same rates, then a higher mass will cancel that effect out, and a higher mass will lead to a slower angular displacement or speed. So that is essentially all of angular momentum, or not all of angular momentum, but all you need to understand for harmonics on a unit circle, I would say. Or actually, it doesn't have to be a unit circle. Harmonics relating harmonic motion and uniform circular motion. So